even if people are still dropping in. But since we like to keep this 1 hour frame, it's better to start now. I welcome everybody today. It's nice to see so many people once again to this in this seminar. Some of you have been there before. You see our presentation slides. This is a Beyond EPICA seminar series where we try to look a little bit beyond the ice core and other marine and terrestrial archives about the MPT. And it's our pleasure that today we will talk about SST and sea surface reconstructions across the MPT. And we have 2 speakers we look forward to, Jeremy Shakun, Boston College, and then in the second talk will be by David Hotel, University of Cambridge. We start with Jeremy, and I'm not sure if I have to introduce him, but for the ones who don't know Jeremy, I mean, Jeremy is a geologist. He has done a master's at the University of Massachusetts and done a PhD at Oregon State University together with Peter Clark. And I think, correct me, Jeremy, if I'm wrong, this is the time where you started to work on analyzing these big data sets and trying to look at the various data sets, bringing them together to understand patterns and mechanisms of past changes. And I saw from your CV, you have done a postdoc. I followed it a little bit at different places, Lamont, Woods Hole University, and also Harvard. And since 2013, you're at Boston College now, first as an assistant professor, and now with your own group since 2019 as an associate professor in the Department of Earth and Environmental Science. Jeremy, we really look forward to your talk, and the floor is yours. I stop my screen sharing here.
Good deal. Thanks, Martin. Let me load this up.
And to everybody, the format is like before. We have a 20-minute talk by Jeremy. Then we have a first time of round of questions, 10 minutes. And then we will switch over to David. Once again, 20 minutes plus 10 minutes. And if you have more questions, the speakers agreed to stay a little bit longer afterwards to answer some questions. So maybe we can do it a little bit after 3 for those people who really like to stay on for maybe 10, 15 more minutes or so. Okay, Jeremy, please.
Okay, all good. Can you see that?
I see your screen.
Okay. Thanks, Martin. Thanks, Emily. Thanks for having me. This looks like a really great seminar series you've been doing this fall, so I'm glad to be part of it. And yeah, I've been working with Peter Clark since my PhD 15 years ago, pulling together big temperature data sets, and still doing it. So that's what I'm going to tell you about. Is we've been trying to get as many SST records around the world together for the Pleistocene as we could find, to look at global variability, to look at regional variability. And this is the kind of project I always find fun to do, because in some ways when you do a big synthesis, you sort of know what you're going to find ahead of time, just seeing enough records, but you don't totally know what you're going to find until you see what falls out. And I think you'll find that's the case here. A lot of what I'm going to show you, you're going to nod and go, yeah, of course, that's what I would have thought, but maybe not everything. And that's kind of the fun part. I think it raises a few questions. So I'll show you our reconstructions in a second, but let me start here, kind of terra firma. Here's the Benthico 18 record. This is kind of my mental model for thinking about Pleistocene evolution, probably for most of you too. And I want to call out, if you look at the Benthico 18 record, you sort of see these 2 steps into the Pleistocene, right? This first drop at the onset of Northern Hemisphere glaciation 3 to 2.5 million years ago. And then there's this second drop down at the mid-Pleistocene transition. And I'll come back to these because we want to see how these are expressed, and I'll compare back and forth in sea surface temperature records around the world. Because of course the Benthico 18 record is complicated, and you can't just take this as a simple reconstruction of climate, right? It's ice volume, it's deep ocean temperature, uncertain ratio between the two that might change through time. And so that's why we wanted to look at sea surface temperature records everywhere, get a more direct proxy for global climate. So we pulled as many together from the published literature to find. We've got about 130 in total. And the map on the left shows you the spatial distribution of these records. You can see we've got about more than half are Elkinone records, a bunch more magnesium calcium, a few faunal records. And everything I'm going to show you is on the LRO4 timescale. If it wasn't published that way, we tuned it to LRO4. So everything is synced up. And then on the right side, you're looking at the kind of the latitude time distribution of record, then there's decent global coverage, records from the northern high latitudes to the tropics to the southern high latitudes across the Plio-Pleistocene. And if you just add all these up through time, that's the lower right. There's about 80 records here for the last couple glacial cycles, and then it decreases to a few dozen records by the time you get to the Pliocene. But in general, we usually found in our work that once you get to a few dozen records, that's usually a pretty good indicator of what global mean temperatures are doing. There's quite a few more records if you include lower resolution ones here. That's the dashed line. These don't help with the orbital variability, but they do help with kind of getting the long-term trends in the stacks. I'm mostly focused on the results with the higher resolution records that resolve orbital variability so we can see what that's doing. So once we had all this together, we wanted to composite them into stacks. And the way we chose to do it was not to reference all of these records to the Holocene, to zero them there. We instead chose to zero everything at 3 million years ago. And the reason we did that is because there's quite a few records that span the Pliocene and then a bunch more that span the Pleistocene. So pinning things at 3 million years ago helps to make sure we're kind of splicing things together well and getting that long-term structure. Once we did that, we did line everything up at the Holocene, chose to zero it there later, but we started everything referenced 3 million years ago. Any records that do not overlap that interval, we just sort of mean shifted onto that preliminary stack, lined them up, and then averaged them in. And the last quick note is that when we combined all these and composited them, we first put them in latitude bins and then averaged them with some latitude weighting just to try to deal with any spatial biases we might have in the data set. So put all those together, and here's the global SST stack we get for the last 4.5 million years. Before I jump into it, one last thing we wanted to do was to try to scale this into a full global mean surface temperature. So we used models to help out with that. The plot on the left is showing a lot of different published model simulations for warmer and cooler than present climates. And it shows how changes in global sea surface temperatures in models scale with the full global mean surface temperature. And you get a steeper relationship because changes over land are larger than over the ocean. So we fit a relationship to this, and then we use that to scale the global SST stack to global mean surface temperature, which of course it looks similar. It comes from the SST stack, but you can see there's larger variability, some different rates of change. So let me walk you through what I think are some of the more notable features of these reconstructions. So first off, on the stacks, I have these black dots here at 2 key intervals. Here's the mid-Pliocene, and then also for the LGM. And of course, those are intervals that have received a lot more focused attention, mapping out SST patterns around the world. And so here's 2 of the kind of latest reconstructions. Here's the PRISM data set, and then here's Tierney et al. A Nature paper from a few years ago using a big data assimilation approach with, I think, almost an order of magnitude more records than we have in our compilation. But it's reassuring to see that our kind of independent reconstruction falls pretty much right through these other reconstructions. So it suggests we're getting the amplitude of change in good agreement with bigger data sets. So let me walk through features that stand out here. And I, on the bottom here, have plotted the time rate of change in orange of the global stack. And then in black is a running standard deviation. So you can see that as a measure of the amount of variability through time, orbital variability. And so what you notice if we look at these kind of 2 steps through the Pleistocene, here's that first step, the onset of northern hemispheric glaciation, and you see not much expressed in the global stack. The rate of change doesn't really change. It just sort of continues the long-term trend downward from the Pliocene. Same thing with the glacial cycle variability. It doesn't pick up at the onset of northern hemisphere glaciation. So we take that as a sign that the initial growth of northern hemisphere ice sheets didn't have much effect on global temperatures. Whatever effect, apparently was more localized around the ice sheets. We don't see a strong expression. In contrast, you move to that second step at the MPT, and that's kind of the biggest feature we see in the global stacks. The rate of change picks up. There's this big acceleration across the MPT, and then likewise the variability really picks up, and you get much larger glacial cycles. And if we just pull out the 41 kiloyear component that's here in orange, you can sort of see that increase in variability through time. but it's actually modulated, this interesting amplitude modulation of the 41K cycle by obliquity, right? Obliquity comes in these kind of million-year bundles of larger and smaller obliquity cycles. You can see that manifested in this amplitude modulation in global temperature. And then the last thing I'll call out here on the global stack is here's a evolutionary power spectrum. And you can see how the frequency changes. So right here, here's this big concentration of variability in the early Pleistocene, all at tilt. And then right at the MPT, there's this jump to the 100K cycle. So again, not surprising what you see in a lot of individual records, but the MPT also has that shift to 100K power in surface temperature. So you put these together, and there's kind of these three key features I think we see at the MPT. This acceleration of cooling of global temperature, increasing variability, and the shift to 100K power. So those are kind of the three hallmarks of the MPT, and I'll return to those in a little bit to think about what might be going on. But one first way to think about how to read these is to look at the spatial expression of the MPT around the world. So let me show you this in a couple different ways. So first off, here's three different stacks at the top, parsing out the data set, the Northern Hemisphere, the Southern Hemisphere, and the tropics. And I'm just showing you the long-term running mean of these just to get out the variability, which would be too noisy to see. But you see the same features I was just pointing out. So in all of the regions, there isn't much change in the rate of cooling at the onset of Northern Hemisphere glaciation, but all of them have this acceleration at the MPT. The second shows the variability through time, same story, not much change in variability at 3 million years ago, but a large rise across the MPT. And then here are the wavelets for each of these three regions, same thing everywhere. There's 41K power all over in the early Pleistocene. It jumps to 100K power at the MPT. So these three hallmarks of the MPT, they're everywhere pretty much. It's worldwide, it's global. I'll show you this in one other way. We parse the data set in lots of ways, but here's long-term running averages of the stacks for different dynamical regions, for upwelling zones along coastlines, for upwelling at the equator, extratropical records, warm pools. Here we pulled out different basins, the Atlantic, the Pacific, split by different hemispheres in the tropics. And pretty much all of these stacks you look at, it's the same story. Not much happens at the onset of glaciation, but pretty much all show an acceleration of cooling at the MPT. So the fact that these signals at the MPT, these three hallmarks, are basically worldwide, we take that as a fingerprint probably for global greenhouse forcing. That seems like the most obvious candidate to explain this. And not ice sheets again, because there isn't much expression at the onset of Northern Hemisphere glaciation. I'll come back to the CO2 in a second as a possibility here. One last thing to mention is gradients in regional temperatures. So here, these three stacks right here are showing meridional gradients. In the Northern Hemisphere is the blue, that's kind of the northern higher latitudes relative to the tropics. The green is the same thing for the Southern Hemisphere, meridional gradient. And then the yellow is the zonal gradient across the tropical Pacific. And these gradients are all run really nicely in parallel over this interval and strengthen through time. And they get stronger and stronger until about the MPT, and then the gradients everywhere stabilize, and we kind of reach a modern distribution of temperatures. So this fits with the idea that in the Pliocene there's these expanded warm pools that sort of contract and the gradients grow through time. Since this is an EPICA crowd, I thought I would toss in just one slide comparing our reconstructions to the ice core records. And so the top one here in blue is our extratropical SST stack in the Southern Hemisphere, kind of closest to Antarctica. And the orange line here is showing the moisture source temperature reconstructed from deuterium excess at Dome Fuji. And you can see it's a really nice alignment, kind of Southern Ocean temperatures lining up nicely with our sort of independent SST reconstruction from the Southern Ocean. The middle is the same thing. It's our SST stack from the Southern high latitudes versus the Dome C site temperature. And then the bottom is, again, Dome C in green versus our global mean surface temperature. So all of these, the ice core, it just falls really closely on top of our stacks. And so potentially, if these correlations hold up, these might provide something of a template for what you would find if you get older, deeper ice cores out there. It'll be interesting to see how they map into the sea surface temperatures as older ice comes up. So let me go back to the MPT and think about what might be going on, since that's kind of the most notable feature in the data set. So obviously, there's a lot of thinking around the 100K cycle, the increasing variability perhaps related to CO2 in the carbon cycle. And there's been suggestions, that perhaps the key thing going on there are changes around the Southern Ocean driving that. There's a couple of references suggesting this in recent years. We want to kind of build on these ideas and throw out an additional hypothesis that maybe that changes in the Southern Ocean carbon cycle explain not just those kind of two hallmarks of the MPT we see in surface temperatures, but maybe also that third hallmark we noticed, which is that acceleration in cooling. So let me kind of build this hypothesis where we've been thinking through, especially as Peter has really worked to build this up. So the idea starts from this SST stack from the southern mid and high latitudes here. And the key thing to note is before the MPT, before 1.5 million years ago, temperatures down there are pretty much always warmer than pre-industrial, always above the zero line. Whereas once you get to the MPT and beyond, temperatures are pretty much always colder than pre-industrial. So I think maybe there's sort of something of a tipping point here, manifesting through sea ice. As you enter this colder world, you have two key effects on sea ice. One, just a larger overall sea ice extent, and then two, that in turn could drive a greater sensitivity to orbital forcing. And then sort of play this causal sequence out. Those connections between the extent of sea ice and Antarctic bottom water formation, and we think in turn that might have increased Antarctic bottom water production and carbon sequestration in the deep ocean associated with it, helping to kind of pull CO2, accelerate that drawdown of CO2, pull this long-term trend down. This is a busy plot, I know, but all of these different records you're seeing here in the second panel are kind of different indicators of the size and the variability in Antarctic bottom water and southern sourced water masses in the Southern Ocean. So for instance, this tan line here is showing Delta 13C stack from the deeper Atlantic. And you can see you get more of these depleted 13C excursions as you head across the MPT into the later Pleistocene, representing probably an expansion of Antarctic bottom water in the Atlantic at the expense of NADW. Likewise, other records here, there's neodymium isotope records, there's nutrient proxies, carbonate ion saturation state. All of them sort of agree in showing this this downward shift, this kind of expansion of Antarctic bottom water. And in turn here's a power spectrum for that Delta 13C record, and it shows that same shift from 40K cycles to the 100K power here in 13C. And other people have built up ideas of what else could be going on around the MPT in the Southern Ocean, feedbacks that could kind of amplify this. So one is increases in dust flux as you cool the Southern Hemisphere, get more dust and iron fertilization. Here's a nice record of iron fertilization from the southern high latitudes. That could increase CO2 drawdown. And then here's a nice record of ice rafted debris to the Southern Ocean, showing an increase in iron deflux, further northward export of icebergs. And as that melts, that can stratify the Southern Ocean, sort of increase the cap on the Southern Ocean, holding the CO2 in more. So you put all that together, perhaps it helps to explain long-term CO2 drawdown, really with this kind of tipping point in southern high latitude temperature. On top of that, that might help to get sort of global cooling initiated, and there could, of course, be other feedbacks, kind of dynamical feedbacks on top of that. These increasing SST gradients I mentioned, colder water upwelling in association with those gradients, sort of changes in the pattern effect of surface temperatures around the world, manifesting in different, changes in feedbacks, water vapor, clouds, et cetera. So maybe you put all that together, that helps to explain kind of the long-term acceleration of cooling across the MPT. So that's a hypothesis we're kind of putting out there and have been playing with. So that's sort of the global sea surface temperature reconstructions that we've been building. One last quick sort of sneak preview I want to leave you with is we've been spending a lot of time after that sort of thinking about this classic question you might already be wondering is, can you take the global temperature reconstruction and use that as a way to pull out the temperature component of the benthic-018 record, get it at a new ice volume sea level reconstruction? And we have spent a lot of our time banging our heads on the wall trying to work through that. And so I'll just quickly show you what we've got. Really quickly, the steps we've taken to build that record up is we've used models to take our sea surface temperature reconstruction and see how that might scale to mean ocean deep water temperatures with models. Then we take that mean ocean temperature and use that to pull that out of the benthic-018 record and give us a residual del-18 of seawater signal, kind of the ice volume signal. And then last of all, we've done some simple modeling with Dave Pollard to think about how ice sheet composition, isotopic composition would change as you're in a warmer world or a colder world, and use that to come up with some scalings to convert the del-18 of seawater record to ice volume or to sea level. So I know that's busy and kind of quick, but I'll show you the sea level record. The main thing to notice is a lot of what we get in our new sea level reconstruction is very much what you would expect, but not all of it. And the kind of the curious, odd thing I will show you stems from the fact that if you just plot up our global SST stack here in black and the LRO4 benthic-018 record in red, they don't sit comfortably together. It's not like temperature is 50% of the benthic record and constant through time. There's clearly sort of some decoupling maybe going on here. And so that leads to an odd result. And so here's the sea level record we get. Like I said, a lot of it looks familiar. Ice ages descend after 3 million. We get 40K cycles in sea level, switching to 100K cycles. But the one really oddball thing is we get these really deep low stands by the onset of the Pleistocene. So at 2.5 million, we're already getting sea levels down at minus 130, minus 150 meters, LGM-sized ice volume. You don't see that in the benthic-018 record, right? There's that big increase, presumably, in ice volume at the MPT. We don't see that. And if that's right, that sort of calls into question a lot of hypotheses for the MPT. So for instance, the regolith hypothesis from Peter and David is that there's this big increase in ice volume due to a change in regolith, right? So once we got this result, Peter was like, well, that's that. The regolith hypothesis is dead. To his credit, he was ready to toss that out there. And the reason we get these low stands, if you're kind of puzzling over this, we spent a while looking at it. Fundamentally, if I go back, it comes from this decoupling between temperatures and the benthic-018 record. And the key thing to see here is LRO4, throughout the early Pleistocene, it's pretty much always below Holocene levels. Whereas our temperature reconstruction, when you get to the early Pleistocene, is pretty much always warmer than Holocene conditions. And so if you think about that, these early excursions in LRO4 towards glacials, these are happening in a warmer world. So temperature can't do much to explain that signal. So it kind of means ice volume has to do all the work to explain that. Added on top of that, if you're in a warmer world, presumably you have more isotopically enriched ice sheets, which means they don't have as much leverage to pull on the ocean seawater signal. And so you actually need even more ice volume than you would at first think to explain a given isotopic enrichment during these glacials. So you put these together and you need ice volume to do most of the work, and you need a lot of ice volume to do it. And that's what leads us to these kind of really deep low stands early on. That's a whole other story for another time, but I wanted to quickly toss that out there for you. So I'll leave it there and just toss up my my summary points, and happy to take any questions. Thanks.